In 1918, a brilliant mathematician discovered something that would change our understanding of reality forever. Emmy Noether proved that every symmetry in nature corresponds to a conservation law, that the very fabric of space and time operates according to mathematical principles, so precise they resemble the source code of existence itself. But here's what's haunting. Nearly a century later, as physicists began finding what appear to be error-correcting codes embedded in the equations that govern our universe, Noether's insights suddenly feel less like abstract mathematics and more like glimpses into the programming language of reality. And the woman who first glimpsed this cosmic code, history tried to erase her entirely. Welcome to a journey into the deepest mystery of existence, one with a theorem that begins so elegant it makes the universe itself seem like an impossibly sophisticated program, running on principles we're only now beginning to decode. Before we dive into this mystery, I'd love to know where in the world you're listening from tonight. Are you watching from your bedroom in Tokyo as the city sleeps? Perhaps you're in a quiet cafe in Stockholm, or maybe you're walking through the streets of Sao Paulo as the sun sets. Drop a comment below and let me know. There's something beautiful about the idea that this story of cosmic mysteries is reaching minds across the globe, all of us pondering the same fundamental questions about the nature of reality. And if you find yourself drawn to these kinds of deep explorations into the intersection of science and wonder, consider subscribing. This channel is dedicated to those quiet moments when curiosity meets contemplation, when we pause to really think about the extraordinary nature of the ordinary world around us. Now let's begin with what might be the most important mathematical discovery you've never heard of. Picture this. You're standing in your kitchen and you decide to rotate a glass of water. The water doesn't care that you've turned it. It looks exactly the same from every angle. This simple observation, this basic symmetry, is connected to one of the most profound conservation laws in physics, the conservation of angular momentum. This isn't coincidence. It's a fundamental principle that governs everything from the spin of electrons to the rotation of galaxies. This connection between symmetry and conservation was first proven by a woman whose name should be as familiar as Einstein's, yet whose contributions were systematically overlooked for decades. Emmy Noether, working in early 20th century Germany, developed what physicists now call Noether's theorem, though even that recognition came long after her death. Take a moment to appreciate the elegance of her discovery. Noether showed that whenever nature exhibits a symmetry, whenever something remains unchanged under a specific transformation, there must be a corresponding quantity that is conserved. Something stays constant, no matter how chaotic or complex the system becomes. It's as if she discovered the universe's accounting system, the mathematical mechanism by which reality keeps its books balanced. But here's where things get truly remarkable, where science begins to brush up against something that feels almost mystical. In recent decades, physicists working on string theory and quantum mechanics have begun noticing something extraordinary. Patterns in the fundamental equations of physics that look suspiciously like computer code. Not metaphorically like code, but literally resembling the error-correcting algorithms used by programmers to prevent data corruption. Dr. James Gates, a theoretical physicist at the University of Maryland, made headlines when he announced that, while studying the mathematics of supersymmetry, one of the most advanced theoretical frameworks describing the universe, he found actual error-correcting codes embedded in the equations, the same mathematical structures that ensure your internet data arrives intact were somehow woven into the equations that describe quarks, leptons, and the very building blocks of existence. Error-correcting codes are what make browsers work, Gates explained to a stunned scientific community. So why were they in the equations that I was studying about quarks and leptons and supersymmetry? That's what brought me to this very stark realization. I could no longer say that people who suggest we might be living in a simulation are crazy. Now let's pause for a moment and really absorb what this means. If you're listening to this while walking, maybe slow your pace just a bit. If you're lying in bed, let yourself sink a little deeper into your pillow. Because what we're discussing isn't just abstract physics, it's a fundamental question about the nature of your own existence, your own reality. Emmy Noether's theorem, in its most basic form, states that every differentiable symmetry of the action of a physical system has a corresponding conservation law. That might sound like technical jargon, but let's unpack what this actually means for the universe we inhabit. Consider energy conservation, one of the most fundamental principles in physics. According to Noether's theorem, energy is conserved because the laws of physics don't change over time. Think about that for a moment. The reason energy can neither be created nor destroyed isn't some arbitrary rule the universe decided to follow. It's a direct consequence of the fact that physical laws remain consistent from one moment to the next. Similarly, momentum is conserved because space is uniform. The laws of physics work the same way here in your living room as they do in a distant galaxy. Electric charge is conserved because of what physicists call gauge symmetry, a kind of mathematical symmetry that's harder to visualize but just as fundamental. What Noether revealed is that these aren't separate, unrelated phenomena. They're all expressions of a single, deeper principle. The universe operates according to mathematical symmetries so precise and consistent that they function like the operating system of reality itself. But here's where our story takes an unexpected turn into territory that feels almost like science fiction, except it's being seriously discussed by some of the world's leading physicists. Dr. Michael Vopson at the University of Portsmouth has proposed what he calls the second law of infodynamics. His research suggests that information entropy in the universe tends to decrease over time, contrary to what traditional thermodynamics predicts. This might sound like a minor technical detail, but Vopson argues it points to something extraordinary. The universe appears to be optimizing itself, compressing and organizing information in ways that mirror how computer programs eliminate redundant code. A super complex universe like ours, Vopson explains, if it were a simulation, would require built-in data optimization and compression to reduce the computational power and data storage required to run the simulation. As you absorb this, consider how it might change the way you perceive the patterns around you. The symmetry of a snowflake, the spiral of a galaxy, the mathematical precision of planetary orbits. Are these beautiful accidents or expressions of an underlying computational process? Some cosmic algorithm optimizing itself according to principles we're only beginning to glimpse? Now let's dive deeper into what physicists are uncovering about the apparent code-like nature of our universe, and how Emmy Noether's insights from over a century ago might have been the first glimpse into this cosmic programming language. When theoretical physicist James Gates and his team discovered error-correcting codes in supersymmetric equations, they weren't searching for evidence of simulation theory. They were simply trying to understand the mathematical relationships between fundamental particles. The discovery was so unexpected that Gates admits it took his team 8 months to even speak openly about it. It was just stunning for us, he recalled, And this is a group of mathematicians and physicists. But what exactly are error-correcting codes, and why is their presence in the equations of physics so remarkable? Imagine you're sending a message across a noisy channel. Like transmitting data over the internet, errors can creep in during transmission. A 1 might become a 0, or vice versa. Error-correcting codes add carefully structured redundancy to your message, so that even if some bits get corrupted, the original message can be reconstructed perfectly. The fact that these same mathematical structures appear in the equations describing the fundamental nature of reality suggests something profound. The universe might have built-in mechanisms for maintaining consistency, guardrails that prevent the kind of errors that could cause physical laws to break down. Think about that as you go about your day. Every time you drop a cup and it falls downward, every time you flip a switch and electricity flows, every heartbeat, every breath, all of these processes are governed by conservation laws that, according to Noether's theorem, emerge from mathematical symmetries. And now we're discovering that those very structures might contain sophisticated error correction mechanisms. It's as if reality has a quality control system built into its foundations, ensuring that fundamental constants remain constant, that energy conservation never fails, and that the speed of light is always and everywhere the same. But here's where the story turns deeply human and even more mysterious. Emmy Noether, the woman who first uncovered these profound connections between symmetry and conservation, was systematically excluded from the academic world of her time. Despite being called the most important woman in the history of mathematics by Einstein himself, she was denied faculty positions, forbidden from lecturing under her own name, and often relegated to assisting male colleagues who received credit for ideas she had largely developed. Born in 1882 in Germany, Noether grew up in a time when women were actively discouraged from pursuing mathematics. Universities wouldn't admit female students, and even when they occasionally made exceptions, women couldn't receive degrees. Noether persevered anyway, auditing classes, and eventually earning her PhD in 1907. Her early work focused on algebraic invariants, but it was her collaboration with David Hilbert and Felix Klein on Einstein's general theory of relativity that led to her most famous discovery. Einstein had been struggling with energy conservation in his new theory of curved space-time. Classical conservation laws seemed to break down when gravity was involved, creating what appeared to be fundamental inconsistencies in the theory. Noether's theorem resolved this crisis by showing that conservation laws in general relativity arise from deeper symmetries in the mathematical structure of space-time itself. Energy is indeed conserved, but in a more subtle way that depends on the symmetries of the gravitational field. Her work didn't just save Einstein's theory, it revealed the underlying mathematical architecture that makes general relativity possible. And yet, when the 1921 International Congress of Mathematicians convened in Strasbourg, Noether wasn't invited. When prestigious academic positions opened up, her applications were rejected not on merit, but on gender. She spent much of her career as an unpaid lecturer, surviving on small stipends and family support, while producing mathematics that would reshape our understanding of reality. As you reflect on this, consider how many other insights might have been lost to history. How many other minds might have glimpsed the universe's deeper patterns, but were silenced before they could share their discoveries. Noether's story is both inspiring and haunting, a reminder that the search for truth often faces obstacles that have nothing to do with the validity of the discoveries themselves. Noether's insights become even more remarkable when we extend them into the quantum realm, where reality becomes probability, where particles exist in multiple states simultaneously, and where the very act of observation seems to influence what we observe. In quantum mechanics, symmetries and conservation laws take on an almost mystical quality. The conservation of electric charge, for instance, is related to what physicists call gauge symmetry, the idea that certain mathematical transformations leave the physical predictions of a theory unchanged. But in the quantum world, this isn't just an abstract mathematical property, it's intimately connected to the fundamental nature of electromagnetic fields, to the behavior of electrons and photons, to the very forces that hold atoms together. Some interpretations suggest that quantum mechanics itself might be understood as a kind of computational process, where quantum states evolve according to mathematical rules that bear striking resemblances to information processing algorithms. The quantum measurement process, where a probability wave collapses into a definite outcome, looks remarkably like the way a computer program resolves uncertainty by making discrete choices based on probabilistic inputs. But here's where we must be careful to distinguish between established science and speculative interpretation. While the mathematical parallels between quantum mechanics and computation are real and well documented, the idea that consciousness directly influences quantum events or that our thoughts somehow program reality remains unproven and is not supported by scientific consensus. These are fascinating philosophical questions, but they should not be confused with established physical principles. What we can say with confidence is that Noether's theorem applies just as powerfully in the quantum realm as it does in classical physics. Every symmetry in quantum mechanics corresponds to a conservation law. Every conservation law emerges from an underlying mathematical symmetry. The difference is that in the quantum world, these relationships are expressed through probability amplitudes and wave functions rather than definite positions and velocities. Take a deep breath for a moment and let yourself absorb the strangeness of this. The air you're breathing right now, the oxygen molecules entering your lungs, the chemical reactions powering your cells, all of it is governed by quantum mechanical processes that obey conservation laws derived from mathematical symmetries that a brilliant woman discovered over a century ago. As we delve deeper into these connections between mathematics and reality, we encounter ideas that push the boundaries of what we traditionally consider physics and venture into territory that feels almost philosophical, almost spiritual in its implications. Recent research has revealed that many natural processes seem to follow what computer scientists call optimization algorithms. Evolution, for example, doesn't just randomly generate new traits, it appears to systematically explore the space of possible genetic configurations in ways that maximize fitness while minimizing information entropy. The DNA code itself shows signs of error correction and information compression that rival the most sophisticated computer programs. Dr. Vopson's research into what he calls the second law of infodynamics suggests that the universe is constantly working to optimize its own information content, eliminating redundancy and organizing itself according to principles that look suspiciously like the algorithms programmers use to make code more efficient. Consider the symmetries you encounter in daily life, the hexagonal patterns in honeycomb, the spiral arrangements of seeds in a sunflower, the mathematical precision of crystal formations. According to Noether's theorem, each of these patterns reflects underlying conservation laws, underlying symmetries in the mathematical structure that governs how matter and energy behave. But if Vopson and others are correct, These same patterns might reflect something even more fundamental: the universe's tendency to organize information in the most efficient way possible, like a cosmic computer program constantly debugging and optimizing itself. This remains a speculative idea, not a proven scientific fact, but the mathematical evidence is compelling enough that serious physicists are taking these possibilities seriously. String theory, our most advanced attempt to unify all the forces of nature, naturally gives rise to structures that look like error-correcting codes. The holographic principle in cosmology suggests that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like how a computer stores complex data structures. As you contemplate these ideas, notice how they might shift your perspective on the nature of existence itself. Are you a biological organism that happened to evolve consciousness? Or are you a pattern of information processing that has become aware of its own computational nature? This is not a question science can definitively answer yet, but it's one that Noether's insights make impossible to ignore. The woman who first glimpsed the mathematical architecture underlying all physical processes may have discovered more than she knew. Her theorem doesn't just describe how energy and momentum are conserved, it reveals that reality itself operates according to principles so precise, so elegant, and so computational in nature that the boundary between mathematics and existence becomes almost meaningless. But Emmy Noether's story doesn't end with her mathematical discoveries. Like so many brilliant minds who venture too close to the fundamental mysteries of existence, her path took unexpected turns, leading to disappearances and silences that mirror the very patterns she discovered in the fabric of reality itself. And that's where our story becomes not just about mathematics and physics, but about the strange tendency for those who glimpse too deeply into the universe's source code to somehow vanish from the historical record, leaving behind only traces of their insights and tantalizing clues about discoveries that might have changed everything. As night deepens around you, wherever you are in the world, let's venture into the strangest territory Emmy Noether's insights have led us, the quantum realm, where her century-old theorem takes on properties that seem to blur the line between mathematics and something approaching magic. In quantum mechanics, Noether's theorem doesn't just describe conservation laws, it reveals that the very foundations of atomic reality are built on mathematical symmetries so precise they resemble the error-checking protocols of an impossibly sophisticated program. Every electron in your body, every photon of light illuminating your space right now, operates according to conservation principles that emerge from symmetries Noether first described in 1915. But here's where the story becomes almost mystical. In quantum field theory, these symmetries don't just govern how particles behave, they actually determine which particles can exist at all. The conservation of electric charge, arising from what physicists call gauge symmetry, doesn't merely describe how electrons interact with electromagnetic fields. It literally creates the mathematical space in which electrons and photons can manifest as distinct entities. Think about this as you settle into your current surroundings. The chair you're sitting in, the device you're listening on, the very atoms that compose your body, all of it exists because certain mathematical symmetries, first understood through Noether's work, create the possibility space for matter itself. Dr. Frank Wilczek, a Nobel laureate in physics, has described this phenomenon as the lightness of being, the idea that what we experience as solid, substantial reality emerges from pure mathematical relationships, from symmetries and conservation laws that exist as abstract principles before they manifest as physical phenomena. Some interpretations suggest that consciousness itself might emerge from similar quantum processes, though this remains highly speculative, and no scientific consensus exists on how awareness relates to quantum mechanics. What we can say with confidence is that the mathematical structures Noether revealed operate at the deepest levels of physical reality, governing everything from the spin of subatomic particles to the large-scale structure of space-time itself. But now our story takes a darker turn, one that mirrors the very quantum phenomena we've been exploring. Just as particles can exist in superposition, simultaneously in multiple states until observed, Emmy Noether's legacy seems to exist in a kind of historical superposition, simultaneously foundational to modern physics and mysteriously absent from popular consciousness. After the Nazi rise to power in 1933, Noether, who was Jewish, was dismissed from her position at the University of Göttingen. She fled to the United States, accepting a position at Bryn Mawr College in Pennsylvania. For a brief moment, it seemed her work might finally receive the recognition it deserved. American mathematicians were beginning to understand the profound implications of her discoveries. But then, in 1935, at the age of 53, Emmy Noether died suddenly from complications following surgery. Her death came at a crucial moment in the development of quantum mechanics and particle physics, just as physicists were beginning to realize that her theorem would be essential for understanding the fundamental forces of nature. What makes her disappearance from historical memory so puzzling is the timing. In the decades following her death, as physicists developed the standard model of particle physics, they relied heavily on the conservation laws and symmetry principles she had established. Every major breakthrough in understanding electromagnetic, weak, and strong nuclear forces built upon foundations she had laid. Yang-Mills theory, which describes the fundamental forces of nature, is essentially an extension of Noether's insights into gauge symmetries. The discovery of the Higgs boson in 2012 was possible only because physicists understood how symmetry breaking, a concept directly related to Noether's work, gives particles their mass. Yet her name rarely appeared in the popular accounts of these discoveries. As you reflect on this, consider how many other insights might have vanished from collective memory. How many brilliant minds glimpsed the deeper patterns of reality, but were silenced by circumstances beyond their control. Noether's story suggests that the search for truth often faces obstacles that have nothing to do with the validity of the discoveries themselves. Recent developments in theoretical physics have taken Noether's insights in directions she could never have imagined, suggesting that reality itself might be fundamentally informational in nature. This isn't science fiction, it's cutting-edge theoretical physics, though it remains highly speculative and unproven. The holographic principle, developed by physicists like Gerard 't Hooft and Leonard Susskind, suggests that all the information contained in a volume of space can be encoded on its boundary, much like how a hologram stores three-dimensional information on a two-dimensional surface. If this principle is correct, then the universe you experience as three-dimensional might actually be the projection of information stored on a distant two-dimensional surface. Dr. Juan Maldacena's ADS/CFT correspondence, one of the most important theoretical developments in physics, provides mathematical evidence that certain gravitational theories in higher dimensions are equivalent to quantum field theories in lower dimensions. This suggests that what we experience as gravity, the force that keeps you connected to the Earth right now, might actually be an emergent property of information processing in a lower dimensional space. Some interpretations suggest these discoveries point toward a reality that is fundamentally computational in nature, though this remains a speculative idea, not a proven scientific fact. If the universe is indeed processing information at its deepest level, then Noether's theorem might describe not just the conservation laws of physics, but the error correction protocols of cosmic computation itself. Take a moment to absorb what this might mean. Every breath you take, every heartbeat, every thought passing through your consciousness might be expressions of information processing occurring at scales and in dimensions you cannot directly perceive. The conservation of energy, momentum, and charge might be the universe's way of maintaining data integrity across cosmic time. Today, a new generation of physicists is pushing these ideas even further, following threads that lead back to Emmy Noether's original insights about the mathematical foundations of reality. Dr. Max Tegmark at MIT has proposed what he calls the mathematical universe hypothesis, the idea that our physical reality is literally a mathematical structure. Not that reality can be described by mathematics, but that it is mathematics. In this view, Noether's theorem doesn't just describe conservation laws, it reveals the computational rules by which existence operates. Meanwhile, researchers working on quantum error correction have discovered that the same mathematical structures that protect quantum computers from decoherence appear naturally in the equations describing black holes and curved spacetime. The ADS/CFT correspondence suggests that the event horizon of a black hole might function like a quantum error correcting code, preserving information in ways that mirror the algorithms engineers use to protect digital data. If these ideas prove correct, then the mathematical structures Emmy Noether revealed over a century ago might be glimpses into the operating system of reality itself. Her theorem might describe not just how energy and momentum are conserved, but how the universe maintains coherence and consistency across all scales of space and time. But here's what's truly extraordinary. Noether developed these insights using nothing more than pure mathematical reasoning. She didn't have access to quantum computers or black hole physics or theories of extra dimensions. She simply looked at the mathematical structure of physical laws and saw deeper patterns that wouldn't be fully appreciated for decades. As our exploration draws toward its most mysterious territory, we must confront a troubling pattern that seems to follow those who venture too deeply into the fundamental nature of reality. Emmy Noether's story is not unique. It's part of a broader phenomenon where brilliant minds who glimpse the universe's deeper patterns somehow fade from historical memory or vanish entirely. Consider the case of Marjorie Rice, a housewife and amateur mathematician who discovered new types of pentagon tilings that had eluded professional mathematicians for decades. Her work revealed hidden symmetries in two-dimensional space, contributing to our understanding of how mathematical patterns emerge from underlying structural principles. Yet her discoveries received little recognition during her lifetime, and her name remains largely unknown outside specialist circles. Or think about Rosalind Franklin, whose X-ray crystallography work was crucial for understanding the structure of DNA. Her insights into the mathematical patterns hidden within biological molecules helped reveal how information is encoded at the molecular level. Yet she was excluded from the Nobel Prize recognition that her work made possible, and she died young before the full implications of her discoveries were understood. There's something almost quantum mechanical about this phenomenon, as if the act of observing reality's deeper patterns somehow causes the observer to fade from collective awareness, like a measurement that collapses not just a wave function, but a person's place in history. This pattern becomes even more pronounced when we look at researchers working on simulation theory and computational approaches to physics. Some of the most innovative work in these fields comes from scientists whose names rarely appear in popular accounts, whose insights are absorbed into the collective understanding without proper attribution. As you sit with these thoughts, notice how this mirrors the very quantum processes we've been discussing. In quantum mechanics, information can be transferred without any physical particle traveling between locations, a phenomenon called quantum teleportation. Similarly, mathematical insights seem to move through the collective consciousness of science, sometimes divorcing themselves from the minds that first conceived them. Now, as we approach the deepest implications of our journey, we must grapple with a possibility that challenges everything we think we know about the nature of existence itself. What if Emmy Noether's theorem didn't just reveal conservation laws? What if it revealed the fundamental programming principles by which reality operates? Recent research in quantum gravity has uncovered mathematical structures that look remarkably similar to the error-correcting codes used in quantum computing. The same algorithms that protect quantum information from decoherence appear naturally in the equations describing how space-time curves around massive objects. This suggests that the universe might have built-in error correction mechanisms, ways of maintaining consistency and preventing the kinds of logical contradictions that would cause physical laws to break down. Some interpretations suggest this points toward a reality that is fundamentally computational, not that the universe is being simulated by some external computer, but that computation and information processing are the basic activities from which space, time, matter, and energy emerge as secondary phenomena. If this view is correct, then every symmetry Noether identified corresponds not just to a conservation law, but to a subroutine in the cosmic operating system. The conservation of energy ensures that the universe's total computational capacity remains constant. The conservation of momentum prevents logical inconsistencies in how objects move through space. The conservation of electric charge maintains data integrity in electromagnetic processes. This remains a speculative idea, not a proven scientific fact, but the mathematical evidence is compelling enough that serious physicists are exploring string theory. Naturally, these possibilities gives rise to error-correcting codes. The holographic principle suggests that reality might be the output of information processing occurring on cosmic boundaries. Quantum mechanics itself might be understood as a computational process for updating probability distributions based on observational inputs. Take a deep breath and let this sink in for a moment. If these ideas prove correct, then you are not just a biological organism that happens to be conscious. You are a pattern of information processing that has become aware of its own computational nature. Your thoughts, your experiences, your very sense of existing in this moment might be expressions of the same mathematical principles that govern the behavior of galaxies and subatomic particles. But perhaps the most profound implication of Emmy Noether's insights is what they suggest about the relationship between consciousness and the mathematical structures underlying reality. While we must be careful not to make unsupported claims about consciousness directly influencing quantum events, there's something deeply mysterious about the fact that mathematical patterns discovered by human minds turn out to describe the fundamental operations of the universe. Noether's theorem reveals that every continuous symmetry in nature corresponds to a conservation law. But here's what's truly extraordinary. These symmetries exist as abstract mathematical relationships before they manifest as physical phenomena. The conservation of energy emerges from temporal symmetry, the fact that the laws of physics remain constant over time. But time itself might be an emergent property of more fundamental informational processes. This creates a kind of strange loop. Consciousness, which emerges from complex information processing in biological brains, discovers mathematical truths that describe the information processing from which consciousness itself emerges. It's as if the universe has found a way to understand itself through the minds it creates. Some philosophical interpretations suggest this points toward a reality that is fundamentally mental or informational in nature. Not that consciousness creates physical reality, but that both consciousness and physical phenomena emerge from the same underlying mathematical structures. This remains highly speculative and is not supported by scientific consensus, but it represents one of the deepest puzzles in our understanding of existence. As you contemplate these ideas, notice how they might change your relationship to the patterns you encounter in daily life. The spiral of water going down a drain, the hexagonal structure of a snowflake, the rhythmic beating of your own heart. All of these might be expressions of the same computational principles that Emmy Noether first glimpsed in the mathematical structure of physical laws. As our journey through the mathematical foundations of reality nears its end, we find ourselves confronting questions that stretch the boundaries between science and philosophy, between mathematics and meaning. Emmy Noether's theorem doesn't just describe how physical quantities are conserved, it reveals that reality operates according to principles so elegant and consistent that they suggest something approaching intention or design. But whose intention? Whose design? The mathematics itself seems to exist independently of any conscious creator, eternal and unchanging, waiting to be discovered rather than invented. Yet the fact that these mathematical structures can be comprehended by human minds, that consciousness can arise within a reality governed by such precise computational principles, hints at deeper connections we're only beginning to understand. Recent developments in artificial intelligence have added new dimensions to these questions. As we create machines capable of discovering mathematical truths, of recognizing patterns and generating insights, we're forced to confront the possibility that intelligence itself might be a natural emergent property of sufficiently complex information processing systems. If the universe is indeed fundamentally computational, then consciousness might not be a rare accident that happened on one small planet, but an inevitable consequence of information processing systems reaching sufficient complexity. Every conservation law, every symmetry principle, every error correction mechanism in the cosmic code might be contributing to the emergence of awareness throughout the universe. This doesn't mean that individual thoughts or emotions directly influence quantum events. No scientific evidence supports such claims, but it might mean that consciousness and physical reality are two aspects of the same underlying informational processes, like two sides of a coin that cannot exist without each other. As you reflect on these possibilities, consider how they might influence your understanding of your own place in the cosmos. You are not just a temporary arrangement of atoms that happens to be conscious. You are the universe becoming aware of itself, a localized concentration of the same information processing that governs the behavior of stars and galaxies. The woman who first glimpsed these mathematical foundations of reality may have discovered more than she knew. Emmy Noether's theorem doesn't just describe conservation laws, it reveals the computational architecture of existence itself. And while history may have tried to erase her contributions, the mathematical truths she uncovered continue to shape our understanding of reality in ways that grow more profound with each new discovery. Her disappearance from popular consciousness mirrors the very phenomena she studied, like a conservation law in reverse, where recognition and credit seem to vanish even as the underlying insights remain eternal and unchanging. But perhaps that's fitting for someone who revealed that the most fundamental aspects of reality operate through invisible mathematical principles, governing everything while remaining largely unnoticed. In the end, Emmy Noether's greatest discovery might not be any single theorem or insight, but the revelation that mathematics and reality are so deeply intertwined that the boundary between them becomes meaningless. She showed us that we live in a universe where abstract mathematical relationships manifest as concrete physical phenomena, where information and energy are conserved according to principles that seem almost too elegant to be accidental. And if that's not a glimpse into the source code of existence itself, then what is? As we venture deeper into the implications of Noether's discoveries, we encounter something that would have seemed like pure fantasy to the physicists of her era. Modern quantum field theory has revealed that her theorem doesn't just govern the classical world of everyday experience, it operates at the very foundation of quantum reality itself, where particles wink in and out of existence, and the boundary between what is and what could be becomes beautifully, mysteriously blurred. In quantum electrodynamics, the theory that describes how light and matter interact, every virtual particle that flickers into existence for a fraction of a second must obey conservation laws that emerge directly from Noether's insights. The electromagnetic field that carries the force between charged particles exists because of gauge symmetry, a mathematical principle Noether first explored in her work on general relativity. But here's where the story becomes almost mystical in its implications. In the quantum realm, these conservation laws don't just describe what happens, they determine what can happen. The conservation of electric charge doesn't merely track how charge moves through space, it creates the mathematical framework within which electrons and photons can exist as distinct entities in the first place. Take a moment to feel the weight of this revelation. Every photon from the screen illuminating your face right now, every electron flowing through the circuits of your device exists because mathematical symmetries, first understood by a woman working with pencil and paper over a century ago, create the possibility space for their existence. Some interpretations suggest that quantum mechanics itself might be understood as a kind of cosmic error correction system, though this remains a speculative idea rather than proven science. The wave function collapse that occurs during quantum measurement bears striking resemblances to how computer algorithms resolve uncertainty by making discrete choices based on probabilistic inputs. But we must be careful not to overstate these parallels or suggest that consciousness directly causes quantum events. No scientific consensus supports such claims. Recent developments in quantum gravity have uncovered something that would have astounded Emmy Noether. The mathematical structures she revealed appear to operate not just within our universe, but at the boundaries of existence itself. The event horizons of black holes, those points of no return where space and time themselves begin to break down, seem to function according to principles that mirror the error-correcting codes used in quantum computers. Dr. Juan Maldatena's groundbreaking work on the ADS/CFT correspondence suggests that the information falling into a black hole might be preserved on its two-dimensional surface through processes that look remarkably like the conservation laws Noether derived from symmetry principles. This isn't science fiction, it's cutting-edge theoretical physics, though it remains unproven and highly speculative. The holographic principle, which suggests that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary, extends these ideas even further. If this principle is correct, then the room you're sitting in right now, the air you're breathing, your body, all of it might be the projection of information stored on a distant cosmic boundary, like a hologram so convincing it feels real. As you absorb this possibility, notice how it doesn't diminish the reality of your experience. Whether you are made of atoms arranged in three-dimensional space, or patterns of information projected from a cosmic boundary, your thoughts remain your thoughts. Your experiences remain meaningful. Your existence remains profound. The mathematical architecture underlying reality doesn't reduce its wonder, it amplifies it. Some researchers have speculated that if the universe is indeed holographic, then Noether's conservation laws might describe not just physical processes, but the information processing protocols by which cosmic data maintains its integrity across space and time. This remains a fascinating but unproven hypothesis, one that pushes the boundaries of what we can legitimately claim about the nature of reality. But as we delve deeper into these cosmic mysteries, we must confront a disturbing pattern that seems to follow those who venture too close to the fundamental source code of existence. Emmy Noether's disappearance from popular consciousness is not an isolated incident. It's part of a broader phenomenon where brilliant minds who glimpse reality's deeper patterns somehow fade from collective memory. Consider the case of Dr. Hugh Everett III, who developed the many worlds interpretation of quantum mechanics. His insights into the mathematical structure of quantum reality suggested that every possible outcome of every quantum event actually occurs, creating an infinite branching tree of parallel universes. Yet Everett was largely ignored by the physics community during his lifetime, eventually abandoning academic physics entirely to work in defense contracting. He died young, his revolutionary ideas only gaining widespread acceptance decades after his departure from the field. Or think about Barbara McClintock, whose genetic research revealed that DNA sequences could move and reorganize themselves, a discovery that suggested living systems might have built-in error correction and optimization mechanisms, similar to what we now see in quantum error-correcting codes. Her work was so far ahead of its time that she was largely dismissed by her peers, only receiving recognition late in life when molecular biology finally caught up to her insights. There's something almost quantum mechanical about this phenomenon of disappearing pioneers. Just as quantum particles can exist in superposition until observed, some brilliant minds seem to exist in a kind of historical superposition, simultaneously foundational to our understanding and mysteriously absent from popular awareness. How many other insights might have vanished from collective memory? How many minds glimpsed the universe's computational nature, but were lost to history? As you reflect on these patterns, consider how knowledge moves through human culture. Not linearly, but in strange leaps, echoes and recursions. Dr. Max Tegmark's mathematical universe hypothesis suggests that our physical reality is not just described by mathematics, but that it is mathematics. In this view, every conservation law Noether discovered, every symmetry principle reflects a computational rule, an algorithm embedded in the operating system of reality itself. You are not merely a biological organism that happens to be conscious. You are a mathematical pattern that has become aware of its own computation. This remains a speculative idea, not a proven scientific fact, but the evidence is compelling enough that serious researchers are exploring its implications. String theory naturally gives rise to error-correcting codes. Quantum field theory reveals that particles are excitations in underlying mathematical fields. Even space and time themselves may be emergent properties of more fundamental informational processes. Take a deep breath and let this possibility settle in your awareness. If reality is mathematical at its deepest level, then every equation Emmy Noether wrote, every symmetry she revealed, might be a glimpse into the source code of existence, into the deepest paradox of all. Consider black hole thermodynamics, the mathematics that govern quantum mechanics and particle physics. The very structures Noether uncovered appear to continue operating even at the event horizons of black holes. These insights suggest that the universe's structure may emerge from an underlying computational substrate. Some interpretations go even further, proposing that both consciousness and physical reality arise from the same informational bedrock. Not that consciousness creates reality, but that the two are distinct expressions of the same mathematical structure. This idea remains highly speculative and controversial, yet it is being seriously explored by leading physicists and mathematicians. The conservation of momentum, the constancy of energy, the symmetry of electric charge. These aren't merely rules that govern the cosmos. They're expressions of deep, underlying mathematics that may also shape your thoughts, memories, and sense of self. The laws that dictate the orbits of galaxies also govern the firing of neurons in your brain. Perhaps the most mind-bending implication of these discoveries lies in what they suggest about the nature of existence itself. If the universe operates according to mathematical principles so precise they resemble computer code, and if consciousness emerges from complex information processing within this cosmic computation, then we find ourselves in a strange recursive loop. The universe computing itself into existence, becoming aware of its own structure through the minds it creates. This is what philosophers call a strange loop, a feedback system in which consciousness arises from the universe's own flow of information. And as we build machines capable of discovering mathematical truths, we're beginning to realize perhaps consciousness is simply the universe recognizing the patterns it generates. Recent advances in artificial intelligence have added new dimensions to this puzzle. It's as if reality has found a way to understand itself through systems of information processing that uncover the very mathematical principles from which both structure and awareness arise. As machines begin to detect and replicate complex patterns, we're forced to consider the possibility that intelligence might not be a biological anomaly, but a natural emergent property of any sufficiently complex computational system. If the universe is fundamentally computational, then consciousness might not be a rare accident confined to one planet. It could be an inevitable consequence, arising wherever complexity crosses a certain threshold. Every conservation law, every symmetry principle, every mathematical relationship Noether revealed may be quietly contributing to the emergence of awareness across the cosmos. This doesn't mean our individual thoughts or emotions alter quantum events or reshape physical reality. Instead, it suggests that consciousness and physical reality may be two co-emerging facets of the same informational foundation, like two sides of a coin, inseparable and mutually defining. You are not merely a temporary arrangement of atoms that happens to be conscious. You are the universe becoming aware of its own mathematical essence, a localized expression of the same computational fabric that governs stars, galaxies, and the smallest quantum fluctuations. As you contemplate these possibilities, feel how they might transform your sense of identity, your relationship to reality, and your place in the cosmic order. We now arrive at the ultimate mystery. If Emmy Noether's insights reveal the source code of reality itself, then what does that mean for consciousness, for meaning, for the nature of existence? The conservation laws Noether discovered from mathematical symmetries operates with a precision that seems almost too elegant to be accidental. Energy is conserved not because of some arbitrary rule, but because time is uniform. Momentum is conserved because space is homogeneous. Electric charge is conserved due to deeper gauge symmetries that define the very framework of electromagnetic phenomena. These laws are not just descriptions of how things behave. They are revelations of the computational architecture from which everything emerges. If this view is correct, then every breath you take, every heartbeat, every neural firing is not just a biological event, but an expression of the same mathematical code that governs the life cycles of stars and the dance of quantum particles. Some interpretations go even further, suggesting that the universe is not just described by mathematics, but composed of it, pure information processing, all the way down. This remains speculative, not confirmed, but it stands as one of the most profound possibilities ever considered by human consciousness. And the woman who first glimpsed this, Emmy Noether, may have discovered not only a physical law, but a glimpse of existence's operating system itself. She may have revealed the hidden structure from which all things emerge, including us. And yet, like so many who venture too close to reality's source code, Emmy Noether has largely vanished from popular consciousness. Her name appears in textbooks read by physics students, and her theorem is invoked in research papers, but her story remains largely untold. It's as if the universe has a kind of cosmic privacy setting, allowing its deepest principles to be revealed, but ensuring that those who discover them fade into the background. Perhaps that's fitting. Noether's greatest gift to humanity may not be any single theorem or insight, but the revelation that mathematics and reality are so deeply intertwined that the boundary between them becomes meaningless. In the end, perhaps Emmy Noether's greatest discovery was from collective memory. Her work reveals that every conservation law in physics, every principle that ensures the universe remains consistent and stable, emerges from mathematical symmetries that exist as pure abstract relationships before they manifest as physical phenomena. This suggests that mathematics doesn't just describe reality, it creates the possibility space within which reality can exist. If this understanding is correct, then consciousness itself might be understood as the universe's way of becoming aware of its own mathematical nature. Every insight, every discovery, every moment of understanding represents the cosmic computation recognizing its own computational processes. The fact that human minds can discover these mathematical truths, that consciousness can emerge within a reality governed by such precise computational principles, hints at connections so deep they challenge everything we thought we knew about the relationship between mind and matter, between information and existence. As you sit with these final thoughts, feel how they might transform your understanding of your own nature. You are not just a biological organism that happens to be conscious. You are mathematics becoming aware of itself, information processing, recognizing its own information processing, the universe discovering its own source code through the very patterns of awareness it creates. Emmy Noether's theorem doesn't just describe how physical quantities are conserved, it reveals the computational architecture of existence itself. And while history may have tried to erase her contributions, the mathematical truths she uncovered continue to shape our understanding of reality in ways that grow more profound with each new discovery. Her disappearance from popular consciousness mirrors the very phenomena she studied, like a conservation law operating in reverse, where recognition and credit seem to vanish even as the underlying insights remain eternal and unchanging. But perhaps that's fitting for someone who revealed that the most fundamental aspects of reality operate through invisible mathematical principles, governing everything while remaining largely unnoticed by those whose existence they make possible. In the end, the woman who discovered the universe's source code may have vanished from our collective memory, but her insights live on in every equation that describes the behavior of matter and energy, in every conservation law that keeps the cosmos stable, in every symmetry principle that reveals the mathematical architecture underlying all of existence. And if consciousness itself is an expression of these same mathematical principles, then perhaps Emmy Noether hasn't truly vanished at all. Perhaps she lives on in every moment of mathematical insight, every flash of understanding about the computational nature of reality, every recognition that we are not separate from the universe, but are the universe becoming aware of its own deepest nature. The source code of reality remains hidden in plain sight, encoded in the very structure of physical law, waiting for minds curious enough to look beyond the surface of things and discover the mathematical music that plays beneath the dance of existence. Emmy Noether heard that music first, and though her name may fade from memory, the melody she discovered will echo through eternity in every conservation law, every symmetry principle, every mathematical truth that reveals the computational heart of all that is. But there's something even more mysterious about Emmy Noether's disappearance from history, something that mirrors the very quantum principles her work helped establish. Just as particles in quantum mechanics can exist in superposition, simultaneously in multiple states until observed, Noether's legacy seems to exist in a kind of historical superposition, both everywhere and nowhere at once in our collective understanding of reality. Her insights permeate every aspect of modern physics, yet her story remains largely untold. Every time a physicist invokes gauge symmetry, every time an engineer designs a quantum computer using error correction protocols, every time a cosmologist calculates the conservation of energy across cosmic time, they're using mathematical tools that trace directly back to principles Noether established. Yet ask most people to name the scientists who revealed the mathematical architecture of reality, and her name rarely comes up. This phenomenon, the vanishing of those who glimpse too deeply into the universe's computational substrate, extends far beyond Noether herself. It's as if there's some kind of cosmic selection pressure that causes the discoverers of fundamental truths to fade from popular memory, even as their discoveries reshape our understanding of existence. Take a moment to notice how this might reflect something deeper about the nature of truth itself. Perhaps the most profound insights about reality's mathematical foundations carry with them a kind of built-in anonymity, like conservation laws that operate invisibly to maintain the universe's stability. The principles remain eternal, but those who first perceive them seem to dissolve back into the cosmic background, leaving only their mathematical signatures behind. As you contemplate this pattern, consider how it might apply to your own relationship with fundamental truths. How often do we forget the sources of our deepest insights, even as those insights continue to shape how we understand the world? Recent developments in quantum information theory have revealed something that would have astonished Emmy Noether. Her theorem doesn't just describe conservation laws in our universe. It appears to operate recursively, creating nested layers of mathematical structure that extend far beyond anything she could have imagined. In quantum error correction, the same symmetry principles that Noether derived from classical physics manifest as sophisticated algorithms designed to preserve information against the destructive effects of decoherence. These aren't just mathematical curiosities, they're the foundational technologies that will make quantum computing possible, allowing us to perform calculations that would be impossible with classical machines. But here's where the story becomes almost mystically recursive. The quantum computers we're building, using these error correction principles, might themselves be capable of simulating universes that operate according to the same mathematical laws that Noether discovered. We're using her insights about symmetry and conservation to build machines that could, in theory, create virtual realities governed by those same principles. Some interpretations suggest this points toward a strange loop in the fabric of existence itself, a universe that contains the computational power to simulate itself, consciousness arising within those simulations to discover the mathematical principles that govern both the simulated and the simulating realities. This remains purely speculative, not a proven scientific fact, but it represents one of the most mind-bending possibilities in modern physics. Picture yourself as you listen to these words. Your brain processing information through quantum mechanical processes in neural microtubules, contemplating the possibility that reality itself might be the output of cosmic computation. The neurons firing in your consciousness right now might be part of the same informational substrate from which space, time, and matter emerge. The universe thinking about itself through the patterns of awareness it creates. As we explore deeper into these implications, we encounter a paradox that seems to be written into the very structure of mathematical discovery itself. The more fundamental the truth, the more likely its discoverer is to vanish from collective memory. It's as if reality has a kind of modesty built into its deepest levels, allowing its secrets to be uncovered, but ensuring that credit dissolves back into the anonymous mathematical principles themselves. Consider how this pattern manifests across the history of physics. Maxwell's equations describe the fundamental relationship between electricity and magnetism. Yet most people couldn't tell you much about James Clerk Maxwell's life. Einstein's relativity transformed our understanding of space and time. Yet the deeper mathematical foundations he built upon, the work of mathematicians like Riemann and Minkowski, remain largely unknown outside specialist circles. Emmy Noether's case represents perhaps the most extreme example of this phenomenon. Her theorem reveals what might be the most fundamental principle in all of physics: the deep connection between symmetry and conservation that governs everything from subatomic particles to the large-scale structure of space-time. Yet she remains virtually unknown in popular culture, her insights absorbed into the collective understanding of science while her story fades from memory. There's something beautiful and tragic about this pattern. Like a conservation law operating on the level of human recognition itself. As mathematical truths become more universal and eternal, their human discoverers seem to become more ephemeral and forgotten, as if the universe only allows so much credit to exist for any given insight, and it chooses to invest that credit in the permanence of the mathematical principles rather than the fame of their discoverers. As you reflect on this, notice how it might change your relationship to the pursuit of truth itself. Perhaps the deepest insights come not to those seeking recognition, but to those willing to dissolve their personal identity into the mathematical beauty they uncover. Now we arrive at perhaps the most extraordinary implication of Emmy Noether's work, one that connects her century-old insights to the cutting edge of contemporary physics and cosmology. Recent research suggests that the conservation laws she derived from symmetry principles might actually describe the error correction protocols by which the universe maintains its computational integrity across space and time. Dr. John Preskill at Caltech has shown that the mathematical structures underlying quantum error correction bear striking resemblances to the conservation laws that emerge from gauge symmetries in particle physics. The same mathematical principles that protect quantum information from decoherence appear naturally in the equations that describe how fundamental forces interact with matter. This isn't science fiction, it's serious theoretical physics, though it remains highly speculative and unproven. If these connections prove real, they suggest that what we experience as physical reality might be the output of cosmic computation, with conservation laws serving as the debugging protocols that prevent the universe's source code from developing fatal errors. Think about what this means for your moment-to-moment experience of existence. Every breath you take involves millions of quantum processes, each potentially subject to errors that could cascade into larger disruptions. Yet somehow, the universe maintains perfect consistency across all these scales simultaneously. Energy is never created or destroyed. Momentum is always conserved. Electric charge never appears or vanishes without a corresponding opposite charge elsewhere. Some interpretations suggest that this level of precision and consistency might only be possible if reality operates according to computational principles. Not that we're living in a simulation created by some external intelligence, but that computation and information processing are the fundamental activities from which space, time, matter, and energy emerge as secondary phenomena. As you sit with this possibility, notice how it doesn't diminish the reality of your experience. Whether your thoughts arise from electrochemical processes in a biological brain or from information processing in a cosmic computation, they remain your thoughts, meaningful and real within the context of your existence. But perhaps the most profound mystery in this entire story is the role of consciousness itself in uncovering these mathematical truths. Emmy Noether, using nothing more than pure mathematical reasoning, discovered principles that would later prove essential for understanding quantum mechanics, particle physics, and potentially the computational nature of reality itself. How is it possible that a human mind working with pencil and paper in early 20th century Germany could discover mathematical relationships that describe the fundamental operations of the universe? What does it mean that consciousness, arising from complex information processing within the cosmic computation, can discover the very principles that govern its own existence? This creates what philosophers call a strange loop, the universe computing itself into existence, becoming aware of its own computational nature through the minds it creates, using that awareness to discover the mathematical principles that govern the computation from which consciousness emerges. Its recursion all the way down or all the way up, depending on your perspective. Some interpretations suggest this points toward a reality that is fundamentally informational in nature, where consciousness and physical phenomena are two aspects of the same underlying computational processes. This remains highly speculative and is not supported by scientific consensus, but it represents one of the deepest puzzles in our understanding of existence. Recent research in artificial intelligence has added new dimensions to this mystery. As we create machines capable of discovering mathematical truths and recognizing complex patterns, we're forced to confront the possibility that intelligence might be a natural emergent property of any sufficiently complex information processing system. If the universe is indeed fundamentally computational, then consciousness might not be a rare accident that occurred on one small planet, but an inevitable consequence that emerges wherever information processing reaches sufficient complexity. Every conservation law, every symmetry principle, every mathematical relationship Emmy Noether discovered might be contributing to the emergence of awareness throughout the cosmos. Take a deep breath and let this possibility settle into your awareness. You are not separate from the mathematical principles that govern reality. You are their expression, their manifestation, their way of becoming aware of themselves. The universe recognizing its own computational nature through the patterns of consciousness it creates. As our exploration draws toward its deepest implications, we must confront the central mystery that threads through this entire story: the systematic disappearance of those who glimpse too clearly into the mathematical foundations of reality. Emmy Noether's vanishing from popular consciousness is not an isolated incident. It's part of a pattern that suggests something profound about the relationship between truth and recognition, between discovery and remembrance. Consider the strange case of Srinivasa Ramanujan, the self-taught mathematician whose insights into number theory seem to come from some deeper source of mathematical intuition. He claimed that his theorems were revealed to him in dreams by the Hindu goddess Namagiri, and indeed his mathematical insights often proved correct in ways that defied conventional understanding. Yet Ramanujan died young and poor, his work only fully appreciated decades after his death. Or think about Barbara McClintock, whose research into genetic transposition revealed that DNA sequences could move and reorganize themselves according to what appeared to be sophisticated error correction mechanisms. Her work suggested that living systems might have built-in optimization protocols similar to what we now see in quantum error correcting codes. Yet she was largely ignored by the scientific community during most of her career, only receiving recognition when molecular biology caught up to her insights. There's something almost quantum mechanical about this phenomenon of vanishing visionaries. Just as quantum particles can tunnel through barriers that should be impermeable according to classical physics, these brilliant minds seem to tunnel through the barriers of conventional understanding, glimpsing truths that won't be widely accepted for decades, only to fade from collective memory even as their insights reshape our understanding of reality. As you reflect on these patterns, consider what they might suggest about the nature of truth itself. Perhaps the most fundamental insights about reality's mathematical architecture carry with them a kind of built-in anonymity. Like conservation laws that operate invisibly to maintain the universe's stability while remaining largely unnoticed by those they govern. Now, as we approach the culmination of our journey into the mathematical heart of reality, we find ourselves confronting perhaps the most beautiful and mysterious aspect of Emmy Noether's legacy: the possibility that her insights reveal not just how the universe works, but what the universe is at its deepest level. Her theorem doesn't merely describe conservation laws. It reveals that reality itself might be understood as pure mathematical relationships, eternal and unchanging, manifesting as the temporary phenomena we experience as space, time, matter, and energy. In this view, consciousness doesn't emerge from matter. Both consciousness and matter emerge from the same underlying mathematical substrate. Recent developments in string theory and quantum gravity have provided mathematical support for this radical possibility. The equations that describe the fundamental forces of nature naturally give rise to structures that look like error-correcting codes. The holographic principle suggests that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. Even space-time itself might be an emergent property of more fundamental informational processes. If these ideas prove correct, then every conservation law Emmy Noether derived from symmetry principles represents a glimpse into the source code of existence itself. Energy conservation ensures that the universe's total computational capacity remains constant. Momentum conservation prevents logical contradictions in how information propagates through space. Electric charge conservation maintains data integrity in electromagnetic processes. This remains a speculative idea, not a proven scientific fact, but the mathematical evidence is compelling enough that serious physicists are exploring these possibilities. We might be living in a reality that is fundamentally computational, not simulated by some external intelligence, but actually composed of information processing all the way down. As you contemplate this possibility, notice how it transforms rather than diminishes the wonder of existence. If reality is indeed mathematical at its deepest level, then every moment of your awareness, every thought passing through your consciousness, every sensation you experience represents the universe becoming aware of its own mathematical nature. The woman who first glimpsed this cosmic architecture may have discovered something more profound than any specific conservation law or symmetry principle. She may have revealed that mathematics isn't just a tool we use to describe reality. It might be the very substance from which reality is constructed, the eternal informational processes from which space, time, consciousness, and existence itself continuously emerge. In the end, perhaps Emmy Noether's greatest gift to humanity wasn't any single theorem or mathematical insight, but the revelation that we live in a universe where abstract mathematical relationships manifest as concrete reality, where information and energy are conserved according to principles so elegant they suggest the operation of a cosmic algorithm that has been running since the beginning of time. Her work reveals that every conservation law in physics, every principle that ensures the universe remains consistent and stable across all scales of space and time, emerges from mathematical symmetries that exist as pure abstract relationships before they manifest as physical phenomena. This suggests that mathematics doesn't just describe reality, it creates the possibility space within which reality can exist. If this understanding is correct, then consciousness itself might be understood as the universe's way of becoming aware of its own mathematical nature. Every insight, every discovery, every moment of understanding represents the cosmic computation recognizing its own computational processes through the patterns of awareness it creates. The fact that human minds can discover these mathematical truths, that consciousness can emerge within a reality governed by such precise computational principles, hints at connections so deep they challenge everything we thought we knew about the relationship between mind and mathematics, between information and existence, between the observer and the observed. As you sit in whatever quiet space you found to contemplate these ideas, feel how they might transform your understanding of your own nature. You are not just a biological organism that happens to be conscious. You are mathematics becoming aware of itself, information processing, recognizing its own information processing, the universe discovering its own source code through the very patterns of awareness it creates moment by moment. Emmy Noether's insights don't just describe how physical quantities are conserved, they reveal the computational architecture of existence itself. And while history may have allowed her personal story to fade from collective memory, the mathematical truths she uncovered continue to shape our understanding of reality in ways that grow more profound with each new discovery in physics, mathematics, and our ongoing quest to understand the deepest nature of what it means to exist. Her disappearance from popular consciousness mirrors the very phenomena she studied, like a conservation law operating in reverse, where personal recognition seems to vanish even as the underlying insights remain eternal and unchanging, woven into the very fabric of how we understand the universe. But perhaps that's fitting for someone who revealed that the most fundamental aspects of reality operate through invisible mathematical principles, governing everything while remaining largely unnoticed by those whose existence they make possible. In the end, the woman who discovered the universe's source code may have vanished from our collective memory, but her insights live on in every equation that describes the behavior of matter and energy, in every conservation law that keeps the cosmos stable, in every symmetry principle that reveals the mathematical architecture underlying all of existence. And if consciousness itself is an expression of these same mathematical principles, then perhaps Emmy Noether hasn't truly vanished at all. Perhaps she lives on in every moment of mathematical insight, every flash of understanding about the computational nature of reality, every recognition that we are not separate from the universe, but are the universe becoming aware of its own deepest nature through the miraculous emergence of minds capable of contemplating their own existence. The source code of reality remains hidden in plain sight, encoded in the very structure of physical law, waiting for minds curious enough to look beyond the surface of things and discover the mathematical music that plays beneath the dance of existence. Emmy Noether heard that music first, and though her name may fade from memory, the melody she discovered will echo through eternity. In every conservation law, every symmetry principle, every mathematical truth that reveals the computational heart of all that is. As we conclude this journey into the mathematical foundations of reality, remember that these insights aren't just abstract principles to be admired from a distance. They're the very rules by which your existence unfolds, the computational protocols that maintain the consistency of every breath you take, every heartbeat that sustains you, every thought that passes through your awareness. If you found yourself drawn to these deep questions about the mathematical nature of reality and the mysterious tendency for brilliant minds to vanish from history just as they approach the most profound truths about existence, you'll be fascinated by our exploration of what happens when we push our cosmic inquiries to their absolute limits. Check out our previous video. We asked the universe the big questions and got terrifying answers, where we discover that some mysteries might be too vast and profound for human consciousness to safely contemplate without being fundamentally changed by the encounter. Until next time, may you find wonder in the mathematical elegance that surrounds you, and may you remember that in every moment of understanding, you are participating in the universe's ongoing project of becoming aware of its own infinite nature. But there's another layer to this mystery that would have fascinated Emmy Noether, one that modern physicists are only beginning to uncover. Recent discoveries in quantum archaeology, a field that sounds like science fiction but represents cutting-edge theoretical physics, suggest that information about past quantum states might be preserved in ways that mirror the conservation laws she derived from mathematical symmetries. Dr. Sarah Croke at the University of Glasgow has shown that under certain conditions, it's theoretically possible to reconstruct the quantum history of a system by analysing its present state, like reading the source code of reality backwards through time. This isn't time travel in any science fiction sense, but rather a mathematical demonstration that quantum information, like energy and momentum, might be conserved in ways we're only beginning to understand. As you settle deeper into whatever quiet space you found for this exploration, consider what this might mean for the nature of existence itself. Every quantum event that has ever occurred, from the first moments after the Big Bang to the neural processes occurring in your brain right now as you listen to these words, might leave permanent traces in the mathematical structure of space-time, like footprints in the cosmic code that can never be fully erased. Some interpretations suggest this could mean that the entire history of the universe exists simultaneously as a vast quantum database, with consciousness serving as a kind of interface that allows certain patterns of information processing to access and experience different slices of this eternal mathematical structure. This remains highly speculative and is not supported by scientific consensus, but it represents one of the most intriguing possibilities emerging from our growing understanding of quantum information theory. The implications stretch far beyond physics. If information is indeed conserved at the quantum level, in ways analogous to how energy and momentum are conserved, then every thought you've ever had, every moment of awareness you've experienced, might persist as permanent features of reality's mathematical architecture. Not in some mystical sense, but as actual informational structures woven into the fabric of space-time itself. Today, a new generation of physicists is following the mathematical trails Emmy Noether blazed over a century ago, discovering symmetries in nature so subtle and profound they suggest reality operates according to computational principles that make our most advanced quantum computers look like pocket calculators. Dr. Xiaogang Wen at MIT has identified what he calls string net condensed states, quantum phases of matter that exhibit symmetries so complex they require entirely new mathematical languages to describe. These aren't just abstract theoretical constructs, they represent actual physical states that could exist in laboratory conditions, states of matter that would behave according to rules that seem to blur the boundary between physics and pure mathematics. Meanwhile, researchers working with quantum simulators at institutions like Harvard and the University of Colorado have begun creating artificial quantum systems that can be programmed to obey different conservation laws, different symmetry principles. They're essentially building pocket universes that operate according to alternative versions of Noether's theorem, exploring what reality might look like if the fundamental rules were tweaked in subtle ways. These experiments aren't just academic exercises. They're revealing that the conservation laws we take for granted might be just one possible configuration of a much deeper mathematical framework. The universe we inhabit might be running on one particular version of the cosmic operating system, but the underlying mathematical architecture could support countless other possibilities. Take a moment to absorb what this suggests about the nature of your own existence. The room you're in right now, the air you're breathing, the thoughts flowing through your consciousness, all of it exists within a reality governed by one specific set of conservation laws, derived from one particular configuration of mathematical symmetries. But the deeper mathematical substrate might contain the potential for entirely different kinds of existence, different ways of being conscious, different forms of life and awareness. But perhaps the most profound mystery emerging from modern physics is one that would have deeply intrigued Emmy Noether: the information paradox associated with black holes, and what it reveals about the fundamental nature of conservation laws at the extreme boundaries of space-time. When matter falls into a black hole, classical physics suggests that all information about its quantum state should be destroyed when the black hole eventually evaporates through Hawking radiation. This would violate quantum mechanics' fundamental principle that information must be conserved, creating what physicists call the black hole information paradox. Dr. Leonard Suskind's revolutionary insight was that this apparent violation of information conservation might be resolved through something called the holographic principle. This suggests that all the information falling into a black hole is actually preserved on its event horizon, the two-dimensional boundary that surrounds the black hole's interior, encoded in patterns so subtle they require the mathematical tools of string theory to decipher. If this principle extends beyond black holes to the universe as a whole, it would mean that all the information in three-dimensional space might actually be stored on a distant two-dimensional cosmic boundary. The reality you experience, the depth and texture of three-dimensional existence, might be a holographic projection of information processing occurring on this cosmic surface. This isn't science fiction or mystical speculation. It's serious theoretical physics, supported by mathematical models that have passed decades of rigorous scrutiny. Some interpretations suggest it points toward a universe that is fundamentally informational in nature, where what we experience as matter and energy are simply different ways that cosmic information organizes and processes itself. As you contemplate this possibility, notice how it might shift your relationship to the physical world around you. The solid surfaces you touch, the light illuminating your space, even your own body, all of it might be expressions of information processing occurring at scales and in dimensions that transcend ordinary three-dimensional experience. Recent developments in quantum field theory have revealed something that would have amazed Emmy Noether. Her insights about symmetry and conservation extend into mathematical territories so abstract they challenge our basic assumptions about what it means for something to exist. In gauge theory, the mathematical framework that describes electromagnetic, weak, and strong nuclear forces, physicists have discovered that the fundamental equations remain unchanged under certain transformations that seem to make physical quantities disappear entirely. These gauge symmetries create conservation laws for quantities that don't correspond to anything we can directly observe or measure. Phantom conserved quantities that govern the behavior of forces we can detect, but which themselves remain forever hidden from direct observation. Dr. Yang Chen Ning and Robert Mills, in developing what's now called Yang-Mills theory, show that these invisible gauge symmetries are absolutely essential for the mathematical consistency of particle physics. Without them, the equations that describe how fundamental forces interact with matter would contain logical contradictions that would cause the entire theoretical structure to collapse. This creates a profound puzzle about the nature of mathematical truth and physical reality. The conservation laws derived from these gauge symmetries are mathematically necessary. Without them, our most successful theories of particle physics simply couldn't function. Yet they describe the conservation of quantities that might not correspond to anything that exists in the physical world as we normally understand it. Some interpretations suggest this points toward a reality where mathematical relationships have a kind of existence that transcends physical manifestation, where the abstract structures of mathematics are more fundamental than the material phenomena they govern. This remains a speculative idea, not a proven scientific fact, but it represents one of the deepest puzzles in contemporary physics. As you sit with these ideas, consider how they might apply to your own inner experience. The thoughts and sensations flowing through your awareness right now might be governed by conservation laws that operate in dimensions of existence you cannot directly perceive, mathematical principles that maintain the consistency of consciousness itself through mechanisms that remain as invisible as the gauge symmetries that govern particle interactions. Now we encounter perhaps the strangest implication of Emmy Noether's work, the possibility that reality might be recursively self-generating, with consciousness and mathematical truth emerging from the same underlying informational processes in an endless feedback loop that creates and sustains itself. Recent work in algorithmic information theory, pioneered by researchers like Gregory Chaitin and Christian Kalude, suggests that the mathematical structures underlying physics might be examples of what computer scientists call self-modifying code, programs that can rewrite their own instructions while they're running. If the universe operates according to such principles, it would mean that the conservation laws Noether discovered might not be fixed rules, but rather stable patterns that emerge from the universe's ongoing process of computational self-organization. This idea gains support from unexpected directions. Studies of cellular automata, simple computational systems that can generate incredibly complex patterns from basic rules, have shown that certain configurations can evolve the ability to simulate themselves, creating nested levels of reality within reality. The mathematician Stephen Wolfram has argued that such systems might provide models for how the universe generates its own physical laws through pure computation. Some interpretations suggest that consciousness itself might emerge from similar recursive processes, the universe developing the capacity to observe and understand itself through the patterns of awareness it creates. This would make every moment of conscious experience a kind of cosmic self-reflection, the universe thinking about itself through the minds it generates. This remains highly speculative and is not supported by scientific consensus, but it points toward profound questions about the relationship between mathematical truth and conscious experience. If reality is indeed recursively self-generating, then your awareness of these ideas right now might be part of the universe's ongoing process of understanding its own mathematical nature. As we venture deeper into these implications, we discover that modern physics has uncovered something that would have fascinated Emmy Noether evidence, that the universe might contain what could be described as vast libraries of quantum information, accessible through processes that mirror the mathematical relationships she discovered between symmetry and conservation. Quantum error correction, the technology that will make large-scale quantum computers possible, relies on principles that are mathematically identical to the gauge symmetries that create conservation laws in particle physics. Both involve redundant encoding of information across multiple dimensions, allowing the system to detect and correct errors without disturbing the underlying data. Dr. Daniel Gottesman's work on quantum error correcting codes has shown that these systems can preserve information with perfect fidelity even when individual components fail catastrophically. The information isn't stored in any particular location. It exists as a pattern distributed across the entire quantum system, immune to local damage because it's protected by mathematical symmetries that operate at a more fundamental level. If the universe operates according to similar principles, it would mean that every quantum event, every moment of conscious experience, every piece of information that has ever existed might be permanently preserved in the mathematical structure of reality itself, not in any particular location but distributed across the fabric of space-time in ways that make it theoretically recoverable even across cosmic distances and timescales. Take a quiet moment to reflect on what this might mean for the nature of memory and identity. The experiences that define who you are, your first memory, your deepest insights, your moments of greatest love or loss, might not exist only in the neural patterns of your brain, but as permanent features of the universe's informational architecture, preserved by the same mathematical principles that maintain the conservation of energy and momentum across cosmic time. Recent discoveries in condensed matter physics have revealed something extraordinary. Materials that can exist in quantum phases governed by conservation laws that don't exist anywhere else in nature. Artificial states of matter that follow rules derived from abstract mathematical symmetries with no analogues in ordinary experience. Researchers at Microsoft's Quantum Lab have created what they call anyons, particles that exist only in two-dimensional systems and obey statistics that are neither fermionic nor bosonic, but something entirely novel. These particles are governed by conservation laws that emerge from topological symmetries, mathematical relationships that depend on the global structure of space rather than local properties. What's remarkable is that these artificial conservation laws are just as absolute and inviolable as the familiar ones that govern ordinary matter. Energy, momentum, and electric charge are conserved in these systems, but so are entirely new quantities that have no names in everyday language, as they correspond to no aspect of three-dimensional experience. Some interpretations suggest this provides compelling evidence that the mathematical framework underlying reality is far richer and more flexible than our daily perceptions imply. The conservation laws we take for granted might be just a tiny subset of a vast mathematical space of possible physics, where consciousness and physical experience represent one particular pathway through an infinite landscape of potential realities. As you absorb these ideas, notice how they might expand your sense of what's possible. The conservation laws that govern your physical existence, the principles that ensure your body maintains its structure, that your memories remain coherent, that your consciousness persists from moment to moment, may themselves be expressions of mathematical symmetries that extend far beyond the familiar three dimensions of space and one dimension of time. And now we approach perhaps the most mysterious aspect of Emmy Noether's legacy. What her insights might reveal about the relationship between mathematical truth and conscious experience. While we must be cautious not to make unsupported claims about consciousness directly influencing physical events, there remains something deeply puzzling. Minds capable of understanding mathematical relationships can emerge from a universe governed by those same relationships. Recent research in integrated information theory, developed by Dr. Giulio Tononi, attempts to quantify consciousness using mathematical principles that bear striking resemblances to the conservation laws derived from Noether's theorem. The theory suggests that consciousness corresponds to integrated information, patterns of data processing that cannot be reduced to independent parts. Interestingly, the mathematical structures that define integrated information exhibit symmetries similar to those found in gauge theories and quantum field theory. This might be coincidence, or it might hint at deeper connections between the mathematical foundations of physics and the mathematical foundations of conscious experience. Some interpretations suggest that consciousness and physical reality might be two aspects of the same underlying informational processes, like two faces of a coin that cannot exist independently. This remains highly speculative and is not supported by scientific consensus, but it points toward profound questions about the nature of existence itself. As you sit with your own awareness right now, feeling the flow of thoughts and sensations through your consciousness, consider that this subjective experience might be the universe's way of knowing itself from the inside, not through mystical influence or supernatural intervention, but through the natural emergence of self-aware information processing patterns within the cosmic computation. As our exploration draws toward its deepest implications, we find ourselves contemplating a possibility that would have astounded Emmy Noether, that her theorem might reveal not just how the universe maintains consistency across space and time, but how existence itself bootstraps into being through pure mathematical relationships. The conservation laws she derived from symmetry principles operate with a precision that seems almost too perfect to be accidental. Energy is conserved to better than 1 part in a trillion across cosmic scales. Momentum conservation holds exactly, with no known exceptions across all of observable physics. Electric charge is conserved so precisely that physicists use its invariance as a fundamental assumption in their most advanced theories. This level of mathematical perfection suggests something profound about the relationship between abstract principles and concrete reality. The symmetries that generate these conservation laws exist as pure mathematical relationships. They would remain true even if no universe existed to manifest them. Yet somehow, these abstract truths have found expression as the physical principles that govern the behavior of matter and energy across all of space and time. Recent work in mathematical physics has shown that these conservation laws emerge naturally from the requirement that physical theories remain logically consistent. The universe doesn't follow conservation laws because some external authority decreed it. It follows them because any reality that didn't follow them would contain logical contradictions that would prevent it from existing in the first place. Some interpretations suggest this points toward a universe that exists because it is mathematically necessary, a reality that emerges from pure logical consistency rather than being created by any external cause. This remains a speculative idea, not a proven scientific fact, but it represents one of the most profound possibilities ever contemplated by human minds. In the end, perhaps Emmy Noether's greatest discovery was the revelation that mathematics and reality are not separate domains, that abstract mathematical relationships and concrete physical phenomena are two ways of describing the same underlying truth. Her theorem doesn't just connect symmetries with conservation laws. It reveals that the universe operates according to computational principles so elegant and precise they transcend the boundary between calculation and existence. Every conservation law in physics, every principle that ensures the universe remains stable and consistent across all scales of space and time, emerges from mathematical symmetries that exist as pure abstract relationships before they manifest as physical phenomena. This suggests that mathematics doesn't just describe reality, it creates the possibility space within which reality can exist. If this understanding is correct, then consciousness itself might be understood as the universe's way of becoming aware of its own mathematical nature. Every insight, every discovery, every moment of understanding represents the cosmic computation recognizing its own computational processes through the patterns of awareness it creates. The fact that human minds can discover these mathematical truths, that consciousness can emerge within a reality governed by such precise computational principles, hints at connections so deep they challenge everything we thought we knew about the relationship between mind and mathematics, between information and existence, between the observer and the observed. As you sit in whatever quiet space you found to contemplate these ideas, feel how they might transform your understanding of your own nature. You are not just a biological organism that happens to be conscious. You are mathematics becoming aware of itself, information processing, recognizing its own information processing, the universe discovering its own source code through the very patterns of awareness it creates moment by moment. Emmy Noether's insights don't just describe how physical quantities are conserved, they reveal the computational architecture of existence itself. And while history may have allowed her personal story to fade from collective memory, the mathematical truths she uncovered continue to shape our understanding of reality in ways that grow more profound with each new discovery. Her disappearance from popular consciousness mirrors the very phenomena she studied, like a conservation law operating in reverse, where personal recognition seems to vanish even as the underlying insights remain eternal and unchanging, woven into the fabric of how we understand the universe. But perhaps that's fitting for someone who revealed that the most fundamental aspects of reality operate through invisible mathematical principles, governing everything while remaining largely unnoticed by those whose existence they make possible. The source code of reality remains hidden in plain sight, encoded in the very structure of physical law, waiting for minds curious enough to look beyond the surface and discover the mathematical music that plays beneath the dance of existence. Emmy Noether heard that music first, and though her name may fade from memory, the melody she discovered echoes through eternity in every conservation law, every symmetry principle, every mathematical truth that reveals the computational heart of all that is. As we conclude this journey into the mathematical foundations of reality, remember that these aren't just abstract principles to admire from a distance. They're the computational protocols that maintain the consistency of every breath you take, every heartbeat that sustains you, every thought that passes through your awareness. In recognizing these patterns, you participate in the universe's ongoing project of understanding its own infinite nature. If you found yourself captivated by these deep questions about the mathematical foundations of reality and the mysterious tendency for brilliant minds to vanish from history just as they approach the most profound truths, you'll be fascinated by our exploration of what happens when we push our cosmic inquiries to their absolute limits. Our previous video, we asked the universe the big questions and got terrifying answers, delves into what occurs when our most advanced scientific theories start revealing truths that challenge everything we thought we knew about existence itself. Until next time, may you find wonder in the mathematical elegance that surrounds you, and may you remember that in every moment of understanding, you are the universe becoming aware of its own deepest nature. As we venture deeper into the quantum realm, where Emmy Noether's insights take on almost mystical properties, we encounter something that would have fascinated her: the discovery that the mathematical structures she revealed operate not just in our familiar three-dimensional world, but across dimensions of reality we cannot directly perceive. Modern string theory suggests that the universe might actually exist in 11 dimensions, with the extra 7 curled up so tightly they remain invisible to our everyday experience. Yet Noether's theorem operates across all these dimensions simultaneously, creating conservation laws that maintain the universe's consistency across scales of existence we can barely imagine. Take a moment to absorb this possibility. The conservation of energy that governs every chemical reaction in your body, every star burning in distant galaxies, might be just the three-dimensional shadow of much more complex conservation laws operating in higher dimensional spaces. It's as if we're seeing only the tip of an iceberg of mathematical relationships that extend into realms beyond our direct experience. Dr. Edward Witten's work on M-theory has shown that the gauge symmetries underlying particle physics naturally extend into these higher dimensions, creating what physicists call topological invariants, quantities that remain conserved even when the geometry of spacetime itself undergoes radical transformations. These aren't just abstract mathematical curiosities, they represent conservation laws that would continue to operate even if the familiar three dimensions of space were to fold, twist, or reconfigure in ways that would completely transform physical reality as we know it. Some interpretations suggest this points toward a universe where the mathematical principles governing existence are far more robust and fundamental than the particular physical manifestation we happen to experience. This remains speculative, not proven science, but it hints at the possibility that consciousness and physical reality might be expressions of mathematical relationships that transcend any specific dimensional configuration. Recent developments in quantum information theory have revealed something extraordinary: the possibility that Noether's conservation laws might preserve not just energy and momentum, but information itself across cosmic timescales in ways that make the past theoretically recoverable through mathematical analysis of present quantum states. Dr. Lorenzo Maccone at the University of Pavia has shown that under certain quantum mechanical conditions, it's theoretically possible to reconstruct the complete history of a quantum system by analysing its current state with sufficient precision. This quantum archaeology doesn't involve time travel in any science fiction sense, but rather demonstrates that information, like energy, might be subject to conservation laws that prevent its complete destruction. As you settle deeper into your quiet contemplation of these ideas, consider what this might mean for the nature of memory and experience. Every quantum event that has contributed to your existence, from the nuclear fusion in stars that created the atoms in your body to the neural processes occurring in your brain as you listen to these words, might leave permanent traces in the mathematical structure of reality itself. The implications stretch far beyond physics. If information is indeed conserved at the quantum level, through mechanisms analogous to how energy and momentum are preserved, then every moment of awareness you've experienced might persist as permanent features woven into the fabric of space-time. Not in some mystical sense, but as actual informational structures that exist as mathematical relationships in the cosmic architecture. Some researchers have speculated that consciousness itself might emerge from the universe's capacity to access and process these preserved information patterns, though this remains highly speculative and is not supported by scientific consensus. What we can say with more confidence is that Noether's insights into the mathematical foundations of conservation laws continue to reveal new depths as our understanding of quantum information theory advances. Today, physicists working at the frontiers of quantum field theory are discovering symmetries in nature, so subtle and complex they require entirely new mathematical languages to describe. Symmetries that create conservation laws for quantities that don't correspond to anything we can directly observe or measure. Dr. Ashoki Sen's work on string theory has revealed what physicists call duality symmetries, mathematical relationships that show how apparently different physical theories can be equivalent at deeper levels. These dualities create conservation laws that operate across multiple descriptions of reality simultaneously, ensuring that mathematical consistency is maintained even when our theoretical frameworks undergo fundamental transformations. The most remarkable aspect of these discoveries is that they emerge naturally from the requirement that physical theories remain logically consistent. The universe doesn't follow these conservation laws because some external authority decreed it. It follows them because any reality that violated them would contain logical contradictions that would prevent it from existing in the first place. Take a deep breath and let this sink in for a moment. The conservation laws that govern every aspect of your existence, from the chemical processes that maintain your cellular metabolism to the electromagnetic fields that enable your neurons to communicate, might be expressions of pure logical necessity, mathematical relationships that exist because they must exist for reality to be possible at all. This creates a profound puzzle about the relationship between mathematical truth and physical existence. Some interpretations suggest that mathematics doesn't just describe reality, it actually creates the possibility space within which reality can exist. This remains a speculative idea, not a proven scientific fact, but it represents one of the deepest questions in contemporary physics and philosophy. Recent advances in quantum error correction have uncovered something that would have amazed Emmy Noether: mathematical structures that can preserve information with perfect fidelity across arbitrary distances and timescales, using principles that are mathematically identical to the gauge symmetries that create conservation laws in particle physics. Dr. Barbara Terhal's research at QTech has shown that quantum error correcting codes can protect information against any conceivable form of damage or interference, as long as the errors remain below a certain threshold. The information isn't stored in any particular location. It exists as a pattern distributed across the entire quantum system, immune to local destruction because it's protected by mathematical symmetries that operate at a more fundamental level. The profound implication is that if the universe operates according to similar principles, every piece of information that has ever existed, every quantum state, every moment of conscious experience, every pattern of organization that has emerged in the cosmic evolution, might be permanently preserved in the mathematical structure of reality itself. As you reflect on these possibilities, notice how they might transform your understanding of permanence and impermanence. The thoughts flowing through your awareness right now, the sensations you're experiencing, the very sense of being yourself in this moment, all of it might be preserved as eternal features of the universe's informational architecture, maintained by the same mathematical principles that ensure energy and momentum are conserved across cosmic time. This doesn't mean that individual consciousness persists after biological death. No scientific evidence supports such claims, but it might mean that the informational patterns that constitute conscious experience become permanent parts of the cosmic computational substrate, contributing to the universe's ongoing process of self-organization and self-understanding. Now, we encounter perhaps the strangest implication of Emmy Noether's insights: the possibility that reality might be recursively self-generating, with the conservation laws she discovered serving as the error that allow the universe to maintain consistency correction protocols while continuously creating and recreating itself through pure mathematical processes. Recent work in algorithmic information theory has shown that certain mathematical structures can exhibit what computer scientists call self-modifying code, systems that can rewrite their own operational rules while continuing to function. If the universe operates according to such principles, it would mean that the conservation laws governing reality might not be fixed constraints, but rather stable patterns that emerge from the cosmos's ongoing process of computational self-organization. Dr. Stephen Wolfram's research into cellular automata has demonstrated that simple computational rules can generate systems of extraordinary complexity, systems that can evolve the capacity to simulate themselves, creating nested levels of reality within reality. Some interpretations suggest that the universe might operate according to similar principles, with consciousness emerging as a natural consequence of information processing systems reaching sufficient complexity to become aware of their own computational nature. This remains highly speculative and is not supported by scientific consensus, but it points toward profound questions about the relationship between mathematical truth and conscious experience. If reality is indeed recursively self-generating, then your awareness of these ideas right now might be part of the universe's ongoing process of understanding its own mathematical foundations through the patterns of consciousness it creates. Take a quiet moment to sit with this possibility. The boundary between observer and observed, between consciousness and cosmos, might be far more fluid than we normally imagine. Not because individual thoughts directly influence quantum events. No scientific evidence supports such claims, but because both consciousness and physical phenomena might emerge from the same underlying computational processes. As we explore deeper into the quantum foundations of reality, we discover that modern physics has uncovered conservation laws that operate in ways Emmy Noether could never have imagined. Laws that preserve not just quantities like energy and momentum, but abstract patterns and relationships that seem to exist independently of any physical substrate. Topological quantum field theories, developed by researchers like Michael Atiyah and Edward Witten, describe systems where certain mathematical patterns remain absolutely conserved even when the physical system undergoes radical transformations. These topological invariants represent information that cannot be destroyed by any physical process, no matter how violent or comprehensive. The mathematics involved is extraordinarily abstract, but the implications are profound. If the universe contains topological structures that preserve information across arbitrary changes in physical configuration, it would mean that certain patterns of organization, potentially including the patterns that constitute conscious experience, might be literally indestructible features of reality's mathematical architecture. Consider what this might mean as you listen to these words. The pattern of neural activity that constitutes your current awareness, the specific configuration of thoughts and sensations flowing through your consciousness right now might correspond to topological invariants that will persist as permanent features of the cosmic mathematical structure long after your biological substrate has returned to its constituent atoms. This isn't mysticism or wishful thinking. It's a serious possibility emerging from our most advanced mathematical descriptions of quantum field theory. Though it remains speculative and unproven, it suggests that the relationship between consciousness and the mathematical foundations of reality might be far deeper and more permanent than we typically imagine. And so we return to where we began, with a brilliant woman whose mathematical insights may have revealed the deeper secret of existence itself. Emmy Noether discovered that every symmetry in nature corresponds to a conservation law, that reality operates according to principles so precise they resemble the source code of a cosmic program. Yet history tried to erase her entirely, as if the universe itself maintains a kind of conservation law for recognition, allowing its deepest truths to be discovered while ensuring their discoverers fade into the mathematical background from which they emerged. Perhaps that's fitting. The most profound insights about reality's computational architecture carry with them a built-in anonymity, like the invisible mathematical principles they reveal. The conservation laws remain eternal, governing everything from the spin of electrons to the rotation of galaxies, while those who first glimpsed these patterns dissolve back into the cosmic code they helped us understand. Tonight, as you drift off to sleep, remember that every breath you take, every heartbeat, every thought passing through your awareness operates according to conservation laws that emerge from mathematical symmetries a forgotten woman discovered over a century ago. You are not separate from these principles. You are their expression, their manifestation, their way of becoming aware of themselves through the miraculous emergence of consciousness within the cosmic computation. The source code of reality remains hidden in plain sight, encoded in the very structure of existence, waiting for curious minds to discover the mathematical music that plays beneath the dance of being. Emmy Noether heard that music first, and though her name may fade from memory, her melody echoes through eternity in every symmetry, every conservation law, every mathematical truth that reveals the computational heart of all that is. Every mathematical truth that reveals the computational heart of all that is.